Okay, so let's continue our discussion related to inductive and capacitive circuits. And if you recall last lecture, we saw that even simple circuits have very useful properties. For example, the simple RC circuit here could remove lots of noise from a signal. And in this case, a parallel combination of R and C could help us to generate a constant DC value from a sinusoidal input, of course, along with the rectifying characteristics of the diode. And we also saw that RC circuits are part of inverters, MOS-based inverters here. The charging, RC charging here is necessary to switch on this particular inverter. Similarly, there's a discharge characteristics of a capacitance here through the transistor over here. So these RC circuits are an integral part of digital circuits, and they're responsible for delays in gates. And so this was, we had seen that these are simple things about capacitors. Capacitor, the relationship between charge and voltage defined by the capacitance here, the current flowing through the capacitance here, I equal to C dV by dt. Then from here we had seen that if, for example, we are under steady state condition when voltages are not varying with time, then the capacitor acts like an open circuit here because dV by dt is 0, so I equal to 0 is like an open circuit. Then capacitors in parallel, they add up. Capacitors in series, they add up in an inverse manner here, right? So these are the things that we had seen about a capacitance here. And similarly, we had seen about an inductor defined by the relationship V equal to L di by dt. Energy stored in an inductor is half Li square. Inductors in series add up. Inductors in parallel, they add up in an inverse manner here. And the other thing was from here, from this relationship, again in steady state, then di by dt equal to 0, so V equal to 0. So 0 voltage, an element with a 0 voltage is like a short circuit here. So inductors under steady state condition act like short circuit compared to capacitors which act like open circuit here. The other thing was from the relationship of I equal to C dV by dt, we can see that because of finite currents in the circuit, there cannot be an instantaneous change in the voltage across a capacitor. So voltage across a capacitor is continuous at there. There cannot be abrupt changes there. Similarly, from this relationship, we can see because of the finite voltages in the circuit, again, di by dt cannot be infinite then, which means instantaneously or over a very short period of time, current through an inductor cannot change significantly. Okay, so current through an inductor cannot change instantaneously. So both this one, current coming from this relationship, and voltage across a capacitor coming from this relationship here. All right, so with this background, let's quickly look at an example and apply some of the concepts that we have learned. So in this case, for example, some circuit is given and we are asked to calculate the current Ix immediately after the switch is opened. So the idea is that the switch is closed for a long time, and in many of these problems is sort of implicit that before the switch is open, the switch is closed, and it has been closed for a very, very long time for steady state condition to prevail. So we are asked to calculate Ix immediately after the switch is opened, okay? So circuit for t greater than 0, after the switch is open, that's the circuit that we get here. 2K resistor here, 2K resistor here, and the capacitor will have immediately after the switch is open, the capacitor will have some voltage here, which we've denoted as plus minus VC0 plus, meaning just immediately after the switch is opened. Now we know that the voltage across the capacitor cannot change instantaneously. So that's why we are to figure out what is VC0 plus, we are trying to find out what is VC0 minus immediately before the switch is opened. So the circuit for t less than 0, before the switch is open, so the switch is closed, and we have a circuit like this. And remember, we are saying that the switch is closed for a long time. So the circuit has been in steady state, and in steady state the current through the capacitor is 0, so that's why we made it open circuit here. But there is a voltage across the capacitor here, which is what we are trying to calculate. What is the capacitor voltage here? So that's easy to calculate. It's a voltage divider, so 2 by 3 multiplied by 6, so 4 volts here. So the voltage across the capacitor is 4 volt. So the idea is that the switch has been closed for a long time, the capacitor has reached steady state, and the voltage across is 4 volt. And then immediately at t equal to 0, we open the switch. So when immediately we open the switch, we have learned that the voltage across the capacitor cannot change instantaneously. So Vc0 plus must be equal to Vc0 minus here. So we can write that out. And so the current then, we can see that the current that will flow is Vc0 plus divided by 4K. This is the net resistor here, so 1 milliampere here. Right, so immediately after the switch is open, the current through this particular resistor is 1 milliampere here. Note that before the switch was opened, so we come back to this circuit and the current is 6 divided by 3K, so 2 milliamperes here. So before the switch is closed, the current in 2K resistor is 2 milliamperes. Immediately after the switch is opened, the current jumps to 1 milliampere here. So the current across the resistor, of course, can change instantaneously. But note that the voltage across the capacitor cannot change instantaneously. Okay. All right. So let's look at a problem which we encounter many times, which is the discharge of a capacitor through a resistor. So we assume that there is a capacitor here which has a certain amount of charge through some means. Maybe there's a circuit here which has charged up the capacitor here. So right now we are focusing on this capacitor at time t equal to 0. The switch is closed, and we would like to see how the capacitor discharges through this resistor R, in the sense that how does the voltage Vc decrease with time. Okay, so of course this is the relationship that we need to keep in mind. The current through the capacitor is C dVc by dt here, and we can easily see that the current through the capacitor and the current through the resistor, they are equal and opposite here. So if we apply, let's say, KCL at this node here, then KCL would be the current leaving the node. The current leaving the node, one current leaving the node is C dV by dt here. The other current leaving the node is V by R here. Okay, so assume that this particular node here is the reference node here. Okay, so not shown here, but is ground. So it's a reference node. So note that you can add up either all the currents leaving the node or currents entering the node. They are all equivalent. Okay, so this is the equation that we obtain for this particular circuit. C dV by dt, Vc by dt plus Vc by R equal to 0 here. And so we can rearrange this equation, dVc by dt equal to minus 1 over RC, the voltage across the capacitor. So this is an example of a very simple first order differential equation. Okay, so in order to solve, let's quickly look at the background of differential equation here. So this is a very simple equation, dy by dt equal to minus ay. And these equations have the solution of the form yt equal to k e to the power st. Okay, so we're not going to justify, but you'll see in a minute. So if this is a solution, we can substitute it back here. So we can differentiate it. We get ks e to the power st and then minus a k e to the power st here. And from here we get s equal to minus a. So if this is a solution to this equation, then s will have a form of minus a here. And so yt, then solution of an equation of this form will become yt equal to k e to the power minus at. And k, of course, we can find out from the initial condition. So for example, if I put t equal to 0, then this term is 1 and y0 will be equal to k. So the solution to this equation here, dy by dt equal to minus ay, becomes yt equal to y0 e to the power minus at. All right, so let's apply that particular. The other thing is we'll also encounter a more general case where we have not just dy by dt equal to minus ay plus a constant term. So let's look at this one, dx by dt equal to minus a1x plus a2 here. So in this case, the solution, general solution, is of the form xt equal to k1 plus k2 e to the power st. And again, if we substitute it here, we will get s equal to minus a1. Okay, so which means that xt equal to, so we're not going to go through this, we've just seen it. So xt equal to k1 plus k2 e to the power minus a1t. And if we look at this equation and we let t go to infinity, then this particular term, of course we are assuming a1 is greater than 0, a1 is positive. So this particular term will go to 0 here, and x at infinity equal to k1. And note that we are solving this equation. We're going to apply it to a circuit where x may be a current or a voltage, and as time goes to infinity, the currents and voltages, they cannot go to infinity. So if K2 is finite and if A is positive, if it's a if A is negative, let's say, so this whole term, then the exponential becomes positive and this term will blow up here. Okay. All right. So we're not looking at that situation. It's not practical for a circuit. So anyway, so A1 is, so this term, as t goes to infinity, this term goes to 0, and x infinity equal to K1. And so we can write that out. The other thing is we can look at value of x at 0. So x0 is x infinity plus K2. And so from here we can calculate K2 will be x0 minus x infinity. And therefore we can write a general expression for solution of this equation here. dx by dt minus a1x plus a2 is xt will be equal to x infinity plus x0 minus x infinity e to the power minus a1t here. Right? Of course, we still have to figure out what is x0, what is x infinity from a circuit, and we'll also have to figure out what is a1. But if you encounter a differential equation, first order differential equation consisting of only the first derivative in the equation, then this is the general form of the solution here. So we will use this. Now note that x could be anything. X could be current. Then we will write it equal to I infinity plus I0 minus I infinity and all that. If x is a voltage, we'll write it for voltage here. Okay, so it applies to x could be anything, current or voltage. Okay, so coming back to this equation here, dvc by dt equal to minus capacitor discharging through R here. And so this is of the form dy by dt minus ay. And we've already seen the solution of this equation is of this kind. This is a simplified version of what we just saw. So it tells us that the voltage across a capacitor will be equal to Vc0 e to the power minus t by Rc here, right? So just a direct correspondence between these two equations. So we need to find out what is Vc0. So if we put t equal to 0 here, we'll get Vc0 here. So you know, immediately after switch is closed, so that is equal to Vc0 plus. But we know that the voltage across a capacitor cannot change instantaneously. So Vc0 plus will be equal to Vc0 minus, and we are assuming that we know what is the voltage prior to switch closing, which we take it as Vi, right? And so therefore my expression then becomes voltage across a capacitor, of course we are saying cannot change instantaneously, so Vc0 minus must be equal to Vc0 plus here. Okay, Vc0 plus here. So and this is what Vi, so we can substitute it here and get the expression here, Vct equal to Vi e to the power minus t by Rc here. All right, so so we know now how a capacitor discharges when it's connected to a resistor. It discharges exponentially in this particular manner here. Okay, so we have this expression, we can plot it out. And so it starts off, of course, at t equal to 0, the value is Vi, and before that we are saying the value is Vi here. And then this is the exponential discharge here. And most of you are familiar with this particular process here. So this term is important. This Rc is what we call as the time constant here. So it is Vi e to the power minus t by tau. And tau is what we call as the time constant of the circuit. So in this case, it's simply R into C here. And so after 1 tau, after 1 time constant, the voltage is fallen to 0.368 of its original value here. Then after 3 time constant is fallen by 95%, and like that, you know, 4 tau and 5 tau, you know, it continuously decreases with time. And if you really want the capacitor to fully discharge or very close to full discharge, maybe you have to go to at least more than 3 tau. So you may have to go to 4 tau or 5 tau. At 3 tau, it is 95% discharged. So there's still 5% charge remaining on the capacitor here, right? Okay, so that's the capacitor discharging. So let's look at a capacitor charging. So in this case, what we have is an RC circuit and we assume that there is no charge on the capacitor, so the voltage across it is 0. And at time t equal to 0, we are going to close the switch. Now we have a voltage source, and the voltage source will start charging the capacitor here. So we would like to find out how does VC change with time. Okay, so again we know this relationship IC equal to C dV by dt here, and application of KCL at this particular node here. If we apply KCL at this particular node, then note that current leaving the node, so current leaving going down is C dV by dt here, and current going left here would be V minus Vs by R here. So sum of currents leaving the node will be equal to 0 here, right? We could have also written, of course, current entering the node from the bottom, current entering the node from the left, would have been the same thing, obviously. So we can rearrange this equation and write it as, we can collect the terms involving Vc together, dVc by dt, the differential form Rc here. So there's only one differential anyway, so we can write this up, dVc by dt plus Vct equal to Vs here. And note that this equation is of the same form as what we discussed in the last couple of slides ago. And therefore, when we were looking at this equation, we said that the general form of the solution is going to be x infinity plus x0 minus x infinity e to the power minus a1t. So let's compare the two equations. If we compare the two equations, so let's take RC. If you look at it, we can take RC, we can divide all of them by RC here. So this RC will come here, and you will see that A1 is nothing but 1 over RC, okay, and which is the time constant of the circuit. And therefore VCT we can write as VC infinity plus VC0 plus minus VC infinity e to the power minus t by RC. So this is a general form of how the capacitor voltage is going to change. We have found out what is this A1, which is the time constant R into capacitance of the circuit. Now, of course, we need to find out what is VC infinity, what is VC0 plus. So these things we still have to find out. Okay. All right. So what is VC infinity? The switch is closed, and we are talking about time going towards very large time. So, and steady state condition, we assume. When you leave it for a long time, the capacitor will get fully charged, and steady state condition will prevail. And in that situation, the capacitor will act like an open circuit. There would be no current flowing. Once the capacitor is fully charged, no current would be flowing here, and the capacitor would act like an open circuit here. So VC at infinity is going to be simply equal to Vs, right? So it's straightforward in this case. So whenever you have to find out what is the voltage across the capacitor at time t equal to infinity, so you'll take the capacitor as an open circuit, okay? Because no current is flowing through it. So we find, and once you create an open circuit, you solve the circuit to figure out what is the voltage across the capacitor. So that's equal to Vs. What is VC0 plus? Okay, so what is VC0 plus? This is the circuit that we have, right? And we are asking what is this voltage across the capacitor just after the switch is closed, okay? And to do that, what we note is that the voltage across the capacitor does not change instantaneously. So VC0 plus must be equal to VC0 minus, right? So what is the circuit, if the capacitor does not have any initial charge, then VC0 minus. So the idea is that before the switch is closed, it's open, there is no source here. So the voltage across the capacitor, if it doesn't have any charge, the voltage across the capacitor must be 0 here. So VC0 minus is equal to 0, and then that must be equal to VC0 plus, okay? Now it's possible that there was some charge on this particular capacitor, and then the voltage across this particular capacitor would have been equal to whatever the charge is Q by C, and then that would have been VC0 minus, and that would have been the same as VC0 plus. In this case, we are told that there is no charge on the capacitor, and therefore VC0 minus is 0 and VC0 plus is equal to VC0 minus and also 0 then. So if we put in all the terms there, then VC capacitor charging with time can be described by this equation. VCT is Vs 1 minus e to the power minus t by Rc. Right, so that's how it charges. So, and tau is the time constant of the circuit here. So if we are given a circuit like this, Rc, and the switch is not shown over here, so the switch is closed at time t equal to 0. So this is how the voltage across the capacitor changes with time. And so this equation is plotted over here. And again, same thing. So we can look at what is the how close is the capacitor voltage to its final value at different times. So at time t equal to tau, it has reached about 63% of its final value. At 3 tau, it has reached 95%. 95% of its final value. At 5 tau, it has reached 99.3% here. So if you're looking for 99%, the capacitor is charged 99%. So you're looking at a time constant of 5 times tau. You'll have to wait that long, roughly, to attain capacitor charge, which is 99% of its final value here, 5 times tau here. But if you're happy, or if your situation demands that you're looking for where it has reached 95%, then 3 tau is the number to keep in mind here. All right, so that's charging of a capacitor. And these are showing basically, in this case, note that time constant R into C is 1 millisecond. So 1 tau is here, 2 time constant is here, 3 time constant is here, 4 is here, and 5 time constant is here. So you can see how the capacitor is charging, and you can sort of visualize at different time constants where the capacitor is with respect to its almost like a final value here. Okay, so that was RC circuits. So let's look at quickly the RL transients when we have a circuit with a resistor and a single inductor. So in this case also, what we are saying is that at time t equal to 0, the switch is closed. And before that, the switch is open and there's no current or anything in the inductor. Okay, so we are assuming that. So we can write a KVL in this particular loop. Vs will be equal to I times R plus L di by dt. That's the voltage drop across the inductor. And we can compare these two equations. So in this case, the X is the current, the inductor current here, I. And we've seen that whenever you have a first order differential equation like this, the general solution to this is xt equal to x infinity x0 minus x infinity e to the power minus a1t here. So if we compare these two equations, we can clearly see that we can calculate a1 from this one here, and we can write the inductor current it is I infinity I0 minus I infinity e to the power minus r by l t here. Okay, so the time constant here, it can be written as e to the power minus t by tau. The time constant here is L by R. In the capacitive circuit, the time constant was R multiplied by C. In this case, it is L divided by R here. And you can check from the units that these have the units of time. Okay. All right, so we have this. Okay, so let's find out what is I infinity, I0, and I0 also. Okay. So what is I infinity? Remember that inductor in steady state is like a short circuit. So we have this switch closed for a very long time, and when you have very long time, the currents have settled down, and currents are not changing with time, and the voltage across an inductor, remember, is V equal to L di by dt, and di by dt is 0. So the voltage across the inductor is 0. So it acts like a short here. So that's why in steady state we have replaced the inductor by a short. In steady state, we had replaced the capacitor by an open circuit. In here, we have replaced it by a short. And so the current at infinity is very simple, Vs by R here. Okay. So we can put this down here in our equation. All right. We also note now we have to find out what is I0. Note that this I0 is I0 plus here. So we note that the current through an inductor cannot change instantly, right? So I0 plus must be equal to I0 minus. And we are saying that before the switch is closed, note that there is an R and an L, and the current through the inductor then is 0 here. Okay, so I0 minus is 0, so then I0 plus must be equal to 0 here. So we put that in our final expression, and we get IT equal to Vs by R, 1 minus E minus T by tau here. So that's how an inductor current, so current across an inductor builds up slowly, and it takes 3 time constants to reach 95% of its final value. If you want to reach almost 99%, then you'll have to wait for 5 time constants. And the time constant tau is equal to the inductor value divided by the resistance in the circuit. Tau will be L by R. Okay, so what about the voltage across the inductor? So this was current across the inductor, IT. So if you want to look at voltage across the inductor, so IT is Vs by R and 1 minus E minus T by tau here. So voltage across an inductor, V is L di by dt, so just take his differential and you get this voltage here. L by R Vs E to the power minus T by tau here. Okay, so the voltage across an inductor decreases here. So the current, so when you press the switch here, the current across the inductor builds up, starting from a 0 value, builds up to its final value of Vs by R. And the voltage across the inductor steadily decreases, and then eventually in steady state, the current is not changing with time, and therefore this becomes a short and the voltage falls to 0 here. Okay. So we have seen simple RC circuit in the charging mode, discharging mode. We just saw that how a inductor charges through, or how an inductor RL circuit, how it behaves when suddenly is connected to a voltage source. And so what about more complicated circuits? For example, in all of these circuits, we have either one inductor or one capacitor. But the circuit itself is more complicated than a single resistor here. For example, in this case, we have an inductor and 2 resistors. In this case, we have an inductor, we have 3 resistors, current source, and like that, we have more complicated circuits. But an important point to note is we are considering only circuits which contain either only one inductor, and we'll see effectively one inductor when we try to solve them, and similarly, effectively one capacitor when we solve them. Note that it can be that, you know, we could have had 2 inductors in parallel. So then we can, of course, combine them up. So effectively one inductor and effectively one capacitor. Okay. So we are talking about those circuits. And we'll see why we are talking about those circuits. Because when you have multiple inductors or multiple capacitors or a combination of inductor and capacitor in general, then the differential equations are no longer first order. They become more complicated, and the solutions also become harder to obtain. So in this particular lecture, we'll confine ourselves to single inductor or single capacitance circuits. But aside from inductance and capacitance, the circuit otherwise can be more complicated. It can consist of dependent sources, independent sources, multiple of them. It can contain resistors, many types of resistors, many kinds of resistors. So those can be there. So how do we solve these circuits here? How do we find out, for example, if we are interested in current flowing here in this inductor, or we are interested in current flowing through this 8 ohm resistor as a function of time, right? How do we do that? Well, that's where our Thevenin's theorem comes into picture here. So the method that we use for solving circuits which consist of either a single capacitor or single inductor is, so let there be a capacitor here and let the remaining full circuit be like this here. Circuit for t greater than 0 after some switch has been closed or open. And so we are talking about circuits of this kind, one single capacitor effectively and one single inductor. So when you have a situation like this, note that it's a linear circuit. We are confining ourselves to linear circuits. So this linear circuit, between these 2 terminals, you can replace it by a Thevenin's voltage and a Thevenin's resistor. So through use of Thevenin's equivalent, any complicated circuit consisting of a single capacitor basically reduces to a simple voltage source and a RC circuit that we have just looked at. Similarly, in this particular case, in this case also, we can transform it into a voltage source and a resistor. So it becomes a simple RL circuit that we just studied, right? So this general form of equation that we found out, that any voltage or current in a single capacitance or a single inductive circuit will be of this particular form. Why? Because it's the first order differential equation. And so it's a general solution of first order differential equation. So the voltage across a capacitor here or the current flowing through the inductor here will follow this particular form here. And tau, we can easily write down, tau will be either equal to L by R Thevenin. So Thevenin's resistance, which we're writing R equivalent here, or R equivalent. So another symbol that we're using is equivalent resistance of this linear circuit here. So R equivalent C or L by R equivalent, right? So that's this thing here. And R equivalent, we have seen that you could find out what is the R equivalent In many cases, if there are no dependent sources, so all you do is remove all the independent sources, and the net resistance between these two nodes becomes the R equivalent or R Thevenin's here. All right, so a more complicated circuit can be solved, can be analyzed by the methods that we've already studied here. So the simple RC charging circuit that we just studied here, or a simple RL circuit that we studied here, all the results of those circuits can be applied to more complicated circuits. Okay, so let's look at an example here. So in this case, we have a resistor, and we have a resistor R1, and we have R2, and we have an inductor, and we have a switch. And so switch is opened at t equal to 0, right? So which means that before t equal to 0, we are assuming that the switch is closed, and it has been closed for a long time. So many times it will not be mentioned. It is implicit in the question that before opening the switch, then the switch is closed. And when nothing is mentioned, it has been closed for a very, very long time. All right. But we are being asked to calculate, let's say, the current across the inductor immediately after the switch is closed. So note that the current always in an inductor will always follow this form, because we have a single inductance circuit. It will always follow this form. So our task becomes three things. We need to find out what is I infinity. So if we want to know what is the current through the inductor at any particular time after opening the switch, we have to find out what is I infinity, what is I0 plus immediately after opening the switch, and what is tau. So these are the things, three things that we need to find out. So for circuit, for t greater than 0, the circuit is very simple. Once you open it, the circuit is simply here. And therefore, tau is simply L divided by R, L by R2 here. So that's straightforward. Then the other thing is infinity. What is the value of current in infinity? So infinity, note that what will happen is in steady state, the inductor acts like a short, right? So as if it acts like a short and you have a 2K resistor, then obviously the current is 0. There is no power source, nothing here. So even if there was some energy stored in the inductor, all that energy gets dissipated through the resistor. And then if you wait long enough time, then there is no current in the inductor, and so I as t goes to infinity is 0. So our solution then become it will be equal to I0 plus e to the power minus t by tau. So we have determined tau, and I infinity we determined, but we don't know what is I0 plus here. What happens to the current immediately after the switch is opened? Now note that for circuit t greater than 0, if I simply look at the circuit, I cannot find out. I don't have enough information, 2K and 100 millihenries. From here, I cannot find out what is the value of I0 plus. Okay, so I need to go back and look at the fact that the current through the inductor, I0 plus is equal to I0 minus here. Okay. So what we do is we go back before the switch is open. So before the switch is open, the switch is closed, right? So we close the switch. And we said it's been closed for a long time. So long time means steady state condition, which means inductor is a short. So we short it, right? We short it here. And we need to find out this current through the inductor here. So note once it's a short, and a short in parallel with 2K, so you can forget about 2K, right? So the current I0 minus, so the current will be just before the switch is open is this I0 minus will be equal to Vs by R1 here. And that would be the same current through the inductor after the switch is open, because the current through the inductor will not change instantaneously. So that's how we find out I0 plus is Vs by R1. So, and this we had already found out. So now we can take this equation and we have all the values I infinity, I0 plus, and we can get the expression here. It is Vs by R1 e to the power minus R2 by L times t here. Okay, so that's how we end up solving this particular circuit here. Okay, so note that when we write something like this, xt equal to x infinity x0 plus minus x infinity e to the power minus t by tau, this expression, it applies to not just the inductor current. This expression applies to the inductor voltage also. The inductor voltage would also follow this form. So note that if I were to write a equation for, let's say, inductor voltage, what I would get is a first order differential equation. and the solution is of this form. Similarly, in general, if I try to find out what is the current through R2, again I will get a first order differential equation, and the solution is of this form. So it's not just the inductor current and the inductor voltage which go like this here. It's any current and any voltage in general goes like this in first order in a circuit with only one single inductor or one single capacitor. Any current and any voltage will in general go like this here. Okay, so that's a general one. Now, suppose you were asked to calculate the voltage across the inductor, right? So what we did was we had calculated the current across the inductor, right? Current across the inductor we had obtained, and we can take, we know V equal to L di by dt. So we could have found out the voltage here. But you could have also applied this here, right? Voltage across the inductor, you may have attempted, let's calculate voltage across the inductor by finding out what is the voltage at infinity, what is the voltage at 0 plus, and what is tau. Well, in that case, you would have been a little bit of a problem because voltage across the inductor is not the same before and after opening the switch. Okay, it's the current which cannot change instantaneously. The voltage can change instantaneously across an inductor. Okay, for example, note that the current look at the voltage across the inductor. So I've plotted here voltage across the inductor. At time t equal to 0, we are switching. So before switching, the voltage across the inductor is 0. And immediately when you open the switch, look at the voltage across the inductor goes to minus 12. Right, so it goes to minus 12. So voltage across the inductor can switch instantaneously, but not the current. So we cannot write, if we were to write this expression in terms of voltage, we could not have written VL0 plus must be equal to VL0 minus. That would have been wrong. That we can only say about the current through the inductor. That's it. We cannot say about anything else in the circuit. Anything else could change instantaneously. We know that the current across the resistor could change instantaneously. Here we are seeing that the voltage across the inductor changes instantaneously from a value of 0 to a value of minus 12. It changes instantaneously, but not the current. So because the current cannot change instantaneously, that makes it easier for us to determine I0 plus here. Okay, so I0 plus will become equal to I0 minus, and I0 minus then we determine using the circuit before the switch is opened. Okay, so let's look at a different problem. In this case, a capacitance problem here. So we are given a circuit with a voltage source and a resistor here and a capacitor here, and then another resistor here and a voltage source here, and we have a switch. And we are saying that the switch closes at time t equal to 0. Before that, the switch is open, and it is open for a very long time. And we want to know what is the current through the capacitor as a function of time. Okay, so our interest is in current through the capacitor, but what we'll do is we'll try to find out what is the voltage across the capacitor here. So we'll write voltage in this particular form here. Why? Because voltage will allow us to use the fact that voltage VC0, the voltage across the capacitor 0 plus must be equal to voltage across the capacitor at 0 minus. So continuity of voltage we'll take advantage of that in order to help solve the circuit. And once we get the voltage across the capacitor, then we can always take I equal to C dV by dt and get the current across the capacitor here. Okay, so that's what we'll do. So circuit for t greater than 0 will be this circuit. So we close the switch and we have a circuit like this here. And we need to find out, remember the unknowns are the voltage across the capacitor infinity, the initial voltage after closing the switch, and tau. Okay, so we have to find out what is the resistance seen by this particular capacitor here, right? So we remove the capacitance here, and we have to find out what is the resistance between these two nodes. And to do that, we remove all the independent sources, we short it, and we short it here. And we look at what is the net resistance between these two nodes. So we see that is 2 ohms in parallel with 6 ohms. Now we could do that, the simplified form, remember when we did Thevenin's and Norton's equivalent, we could do that because there are no dependent sources. If there had been some dependent sources, then the determination of Thevenin's, this is R equivalent, is nothing but Thevenin's resistance. So what you could have done is remove the capacitor here and found out what is the open circuit voltage here, and you could have found out what is the short circuit current here. So opening it, you could have found out VOC, and then shortening it, you could have found the short circuit current. All right, so you could have done that. So anyway, tau will be equal to C times net resistance here, which is equivalent to here, RC times here. So that we have determined. So next we need to find out the voltage long after closing the switch as t goes to infinity. So the switch is closed. The switch is closed, right? And we are saying t equal to infinity, which means that everything is settled down and nothing is changing with respect to time. That's what steady state means, right? So the capacitor is like an open circuit. So we open it out. And then we need to find out what is the voltage across the capacitor. So it's a simple circuit. And you can verify that this is equal to 25 by 4 here. Right, so that's simple. To find out V0 plus, we note that capacitor voltage does not change instantly. So it will remain the same before the switch was closed. So we go back to the circuit before switch was closed here. T equal to t less than 0 here. So note that if the switch is open, this part of the circuit doesn't matter here. And we are left with this part here, okay, which is here. And so we find out what is the voltage across the capacitor. Remember that the circuit is in this condition for a very long time. So this is open. So this is open here. And the voltage across the capacitor then is V0 minus is 10. And because the voltage is continuous, so V0 plus is also equal to 10. So thereby, now we can plug it into our original equation and we get the voltage across the capacitor, which is given by this expression. And we wanted current, so you can take a derivative, C dV by dt, and you can get the current flowing through the capacitor here. Right, so this is the procedure that in general we follow for finding out what is the voltage across the capacitor or what is the current flowing through an inductor. And once we do that, then other things in the circuit can also be determined. Okay, so for example, how do we find voltages and currents elsewhere in the circuit? So suppose using the method that we just talked about, you determine the voltage across the capacitor or you determine the current across the inductor. What about other voltages and currents? Okay, right, so a general circuit consisting of one capacitor, one inductor, and you found out VC or you found out IL. What do you do next? Well, what you can do is you take this VC out, you found this value here, and you replace it by a voltage source equal to VCT. And in this case, you found the inductor out, you replace it by a current source, which is ILT here, ILT, so put ILT here, okay? So now, note that a capacitor is out and you are a voltage source, and an inductor is out and you have a current source. So you have a normal circuit with voltage sources and current sources. Solve it to get any value that you want. Similarly, you have a normal circuit consisting of voltage sources and current sources with one additional current source. Now, why are the two equivalent? Well, note that as far as the rest of the circuit is concerned, all that matters is what is the voltage across these two pair of terminals here. And that's what we have done. We have put a VCT here. The same voltage that we calculated properly by taking into account everything we calculated, and now we replace it here. Right? And the same current for the rest of the circuit doesn't really matter whether it's an inductor or anything here. All that it matters is what is this current going from here between these two nodes. And if we put in the same value of current, for the rest of the circuit, it doesn't matter. And so you can use this to calculate all the currents and voltages elsewhere in the circuit. Okay, so as an example, let's look at this one here. So this is a slightly complicated circuit. So we want to find out the current in 8 kilo ohm resistor here, this one, as a function of time after the switch here is opened, right? So initially the switch is closed and closed for a long time, and then suddenly the switch is opened. And now we want to know what is the current here. So note our interest directly is not in the current in the inductor. Our interest is in the current in the 8 kilo ohm resistor here. But what is our procedure? Well, our procedure is we first find out what is the current in the inductor, because we have a now established process of finding out what is the current in the inductor. After I find what is the current in the inductor, I will take this inductor out and put a current source of that particular value here. And then the circuit will become a normal linear circuit with current sources and all that. And then we will figure out what is the value here. Okay. So let's do that. So let's find out ILT here. So to do that, note we have a procedure, so I'm not going to go over it. So what you do is switch is opened here, and so you write down ILT equal to IL infinity plus IL0 minus IL infinity e to the power minus t by tau. Tau will be equal to L1 by R equivalent. So all those things you have to follow. And let's say you get this expression here. Okay. So now what we do is, as I've been saying, this, so the switch is open, right? So we keep R2 here, R1 here, R3 here, and we take the inductor out and we replace it by current source. What is the value of this current source? This is here, 0.34 e to the power minus t. It's a time-dependent current source, but it's a current source here, right? And now we need to find out what is the current flowing in the 8K resistor here, right? So now you can see that this one is a simple current division problem here. This current is going to partly flow here and partly flow. These R2 and R1 are in series. So these are like 20 ohm resistor here, and this is 5K. So the current is going to divide between these two. So ILT 5 by 5 plus 20, 0.069. So that's how we find out what is the current flowing here, right? So once you find out a inductor current, well, all other currents and voltages you can find out, okay? Anything else in the circuit would be available to you. Just take the inductor out and replace it by this here. All right, can we solve a two capacitor problem using our present approach? So I've said that in general, no. But let's say you're given a circuit like this with C1 and C2, two capacitors here. So even though it has two capacitors, but note that we are talking about circuit before, let's say, opening the switch, and circuit after closing the switch. And if in each case you end up with circuits consisting of only one capacitor, then you could do it. For example, in this case, you're opening the switch at t equal to 0. So, circuit for t greater than 0. So you've opened the switch, and for t greater than 0, you will have, note that you will have either this circuit or this circuit here, right? So the two circuits separate out. So you have only single capacitance circuit. And let's say you're interested in VC2. So once you open the switch, you have a circuit like this here. So it's a single capacitance circuit, and you could solve it using, the method that we have just talked about. So from here, you can find out what is tau. You can also find out what is VC2 at infinity, because note that ultimately what will happen is the capacitor voltage will, looking at the circuit, capacitor will get completely discharged. There's nothing else here. So VC2 infinity will go to 0. Now you have to find out what is VC2 0 plus. Now 0 plus is equal to what is VC2 0 minus here, just before opening the switch. So we go back to circuit just before opening the switch here. So this is our circuit here. Just before opening the switch, well, this is the circuit that we have. Oh, sorry, before opening the switch, which means the switch is closed. So this is the circuit that we have. But note that we don't have to solve this circuit as a function of time. We are only looking at VCT to 0 minus. And we are saying that the switch is closed for a long time. So when you say switch is closed for a long time, the C1 and C2, they become open circuit. C1 and C2 become open circuit, and you can find out what is VC2 0 here. So that's straightforward. You can easily calculate what is VC2 0 here. Okay. So there are times when you have apparently, two capacitors. You may have a capacitor and an inductor, but when you try and solve it, you'll find that it ends up with a single capacitance or a single inductor. And in the time domain in which you are interested in which you want to find out as a function of time, right? So then you can work it out. Will our approach work here? Okay, look at this particular circuit. So we are again interested in the voltage across the capacitor C2, and we close the switch at time t equal to 0. So what happens now? Well, because for t greater than 0, so you close the switch, you have two capacitors there. And you want to solve this circuit as a function of time. So when you have two capacitors as a function of time, well, then our method will fail. It's no longer a first order differential equation. The solution that we have just written out doesn't work. So let me show it to you. Okay, what happens when there's more than one storage element here? So let's look at this case here. So at time t equal to 0, let's say the switch is closed, right? So let's write a mesh here and two equations here. So Vs equal to I1 R1 plus the voltage across the capacitor here. Vc1, the voltage Vc1 equal to I2 R2 plus Vc2 here. So we can write that out. I1 minus I2 is C1 dV1 by dt. So this is a reference node. Take it as ground. And I2 will be equal to C2 dV2 by dt, current flowing through this capacitor here. And we can combine all of these together into an equation of this kind here. And note that if we combine all of them and we are focusing on VC2 here, You can check it out. You're focusing on the capacitance voltage across this one here. Note that it's a second derivative here, d square Vc2 by dt square, then the first derivative here and this. And general solution, second order differential equation will have two exponentials like this, E1S1t and E2S2. So it's a more complicated solution. And obviously you can see that our method is failing. Our method was Vc was k0 plus k1 e to the power s1t. We had a first order differential equation. So when you have two capacitors in general, you'll get a second order differential equation. Similarly, when you have a C and an L, you'll get a second order in general differential equations, and things become more complicated as you add more capacitances and more inductors in the circuit. Things become more complicated. Sometimes we can simplify because one capacitor may be dominant or one inductor may be dominant, and we could simplify the circuit and get the answer. But the answers become progressively difficult when you have more and more capacitors or more inductors. And then we need to take recourse to simulation to understand and look at the circuit here. Okay. So we'll leave you with this particular problem. We are not asking you to solve this problem. So what we are saying is we have a 3 capacitance circuit. Time t equal to 0, the switch is closed. And we are asking which one represents. So we have shown you 2 curves. We have shown you 2 curves with voltage as a function of varying with time. So we want to ask which one do you think is the voltage across C3 and which one is the voltage across C1 out of these 2. Okay. So think about it, find out, justify it, and so we'll continue our discussion. We'll briefly look at some more inductive and capacitive circuits. And so far we've been looking at these circuits in time domain. We'll start looking at them in frequency domain also. Okay, so let's stop here.